Hi, my name is Tyrel. I'm going to be talking to you today about photon momentum, and because of our understanding of it, where we can apply that. Now, a lot of people don't realize that photons have momentum. One of the biggest reasons is because the formula we're familiar with for momentum is momentum equals mass times velocity. Now, photons, mass is equal to 0. So according to this formula, the momentum of a photon would be 0. But photons react in ways that are not normal. So this equation doesn't work for photons. There's a different equation we use to calculate the momentum of photons. It's equal to Planck's constant over the wavelength. And that gives us a momentum. Now this momentum is extremely small, and it's inversely proportional to the wavelength. So the longer the wavelength gets, the less momentum you have. The shorter the wavelength gets, the more momentum this photon will have, which makes sense because we know that long wavelengths generally we classify as having less energy, and shorter wavelengths have higher energy. So that checks out. Now, one of the things that this tells us is that this momentum in the photon could be transferred. And people have observed this for hundreds of years. One example of this observation is the tail of a comet. So if you have a comet and it's traveling in a direction, the tail of the comet is not in the opposite of the direction it's traveling. It actually is the opposite in the direction of the closest sun. So you've got the sun here, and when we observe this comet, the tail comes in a direct line from the sun, not in the direction the comet's traveling. This led people to believe that the sun or light had some kind of pressure or force that exerts onto the dust and ice and particles that come off of a comet and force that tail away from the sun. So we see that there was some kind of, they've seen for hundreds of years that there was some kind of effect that light was having on comets and these small particles surrounding the comets. Now people have taken this understanding and decided, we could do something else cool in space with photon momentum. So they've been developing something called solar sail. Now solar sailing is a revolutionary way of propelling a spacecraft through space. A solar sail spacecraft has a large, extremely large, reflective sail that is used to capture the momentum of light from the sun and to use that momentum to push a spacecraft forward. So you've got this giant spacecraft, and attached to it, you've got this giant sail, and attached to it is some kind of a spacecraft. Now, the material for the sail is very important because it's got to be large enough to capture these photons. And as we talked about, the pushes from photons, the change in momentum is very slight. But in a vacuum of space where a spacecraft will be located, it's possible that every little push from that photon changes the sail's speed. So when the solar sail faces the sun directly, photons push the spacecraft away from the sun. A solar sail can move a spacecraft in other directions simply by changing the angle of the sail, just like a sailboat would use the wind to travel in different directions. So the sail, that's one of the biggest issues so far with solar sailing. Normally spacecrafts gain their momentum when they're launched from the Earth. There's fuel on the Earth that it burns and pushes a rocket that'll push a spacecraft into space. Of course, that chemical rocket, that fuel, takes up a lot of weight, which is one reason why solar sailing can push a spacecraft theoretically to speeds unattainable by just using the normal propulsion methods for spacecraft today. The more rocket fuel you have, the more weight, and that limits how far a spacecraft can go. So using the solar sail method and having no fuel on board, you use the sun to propel the spacecraft forward and to reach its destinations. A solar sailing spacecraft can continue accelerating as long as there's light pushing it. That means that a solar sailing spacecraft could technically travel forever. Now, of course, there's other forces that will affect it, and there's problems still. Building a solar sail, especially a very large one, is a feat that still needs developed, and it'll take a lot more research and development to find something that will really make it feasible and possible. There's a book called Solar Sailing that says that a solar sail that is 1 square kilometer will create a force of 9 newtons. Nine newtons is not a very large number. Now you can do some math, and with spacecraft currently today, they weigh about 80,000 kilograms. Spacecraft of the future, especially if it's designed for solar sail traveling, will probably weigh a lot differently. But just for the, for the sake of this kind of thought experiment, if you've got a spacecraft that weighs 80,000 kilograms and you have a force of 9 newtons, you're only going to get an acceleration of, let me make sure I get this number right, 1.127 times 10 to the negative 4th meters per second squared. That's a very small acceleration. That's not going to get you anywhere fast. NASA launched a spacecraft in 2018 that will become its fastest spacecraft to date. The spacecraft is actually launched towards the sun. It's a solar probe. And by the year 2024, the spacecraft will reach speeds of 692,000 kilometers per hour. It's a huge speed. So if we've got a spacecraft that's a solar sailing spacecraft, if it starts in our solar system, not in our solar system, but just outside of our Earth's atmosphere, with a 1 kilometer square sail, we've got 9 newtons of force behind it, and that acceleration of 1.127 times 10 to the negative 4th meters per second squared. In order for a spacecraft to reach that speed, it would take 2,500 days. It may seem like a long time, but honestly, it's not that long. There will be other forces affecting it, and a lot of other calculations have to go into it. But with solar sailing, you can reach speeds as fast as NASA's fastest spacecraft. If you think about space travel, we're thinking extremely long times. And as a spacecraft travels, it's still going to need a source of light behind it to propel it. And so you're not going to be able to go in a straight line. You're not going to be able to have the same speeds. But once you've reached certain speeds, you could travel extremely long distances. So solar sailing is a very interesting application of photon momentum. There's another really interesting another application of photon momentum that goes from not a cosmic scale, but a very, very, very small scale. It's called optical tweezers. Using principles we've already learned in our physics class, you can create a sort of trap. This trap, or these optical tweezers can trap dielectric spheres, viruses, bacteria, living cells, organelles, small metal particles, even strands of DNA. Extremely small things. How it works is you've got this source of light, this laser source, and you've got a couple of lenses. So you've got the source of light coming through this lens. This will refract. Excuse my crude drawing. But once it goes through these lenses, these photons will intersect at this point. And at that point right here, you've got forces that'll create a trap. And trap some of those things I mentioned: viruses, dielectric spheres, small particles, small metal particles, things that are extremely small, have very small mass, Because of that small mass, the light momentum, the small momentum transferred from photons creates this trap right here. One of the two of the main uses for optical traps have been the study of molecular motors and the physical properties of DNA. So these are all possible because of our understanding of photon momentum. Where else can we go with this? Who knows? We've got applications in the smallest spaces we can imagine, and we've got applications into the cosmos. So obviously the sky is not the limit with this. Thanks for watching.